See, I think I'll take mine off of my Dropbox because it'll run as a PowerPoint better. Okay, talking about other graphs. The graphs we have talked about so far have been pie charts, bar charts, Pareto charts, and histograms. Okay? Some other kind of graphs that you may run across. First one is a multiple bar graph. A multiple bar graph is useful if what you're trying to compare is two sets of data that are somehow kind of related to each other. Maybe it's the same measurement, but it's taken from two different periods in time. Or maybe it's you're comparing male scores to female scores, or freshmen to sophomores, but you're comparing different, it's the same measurement, kind of from different groups. So this is the age group of women, and the bars are representing the number of women who were never married. And the interesting thing here is you notice that these dark purple bars are all taller than the lighter purple bars. So what we would take away from that is that in number one, in 2000, there were a lot more women that were unmarried at every age than there were in 1970. Okay? The other takeaway would be that in 2000, the number of women that weren't married was highest in the 20 to 24 category. So those women were younger and had not married yet. Maybe they were waiting, maybe they were choosing not to get married, maybe they were working on careers. That drops by almost half as soon as you get to the next age group, 25 to 29. And then it drops into half again, or pretty close to half, by the time that they're in their early 30s. By the time they're in their late 30s, all the way into their late 40s, that's a lot smaller number of women than it was when they were in their 20s. So most of those women have gotten married over that period of time. In 1970, the difference is that 20 to 24 was still the higher category. By the time they had gotten to be 25 to 29, they had dropped down to less than a third of that. And then from 30 to 34, 35 to 39, and 40 to 44, it was all pretty much the same. So in 1970, the unmarried women dropped off a lot quicker as they got older. Whereas in 2000, it dropped a lot slower among the age groups. You also have something called a multiple line graph. This multiple line graph actually represents automobile fatalities, so people that died in car wrecks, and the different colored lines represent details about the accident. The blue line, which is the one at the top, interestingly enough, is the one where no alcohol was involved, which is kind of contrary to what we usually think. But the next highest one, at least at the beginning in 1982, the next highest one was where there was a lot of alcohol involved. And notice here that over time, the accidents where there was no alcohol involved, those increased from 1982 to 2000. But the ones where there was a lot of alcohol involved, they actually decreased at about the same rate that the ones that involved no alcohol at all. And all the way through from 82 to 2000, the ones where there was moderate alcohol involved was the lowest, and it stayed pretty steady. Now we do notice that overall, yes, if you look at your beginning points compared to your ending points, the no alcohol and the moderate alcohol pretty much did, the no alcohol increased, but the moderate alcohol didn't increase, it decreased, and so did the high alcohol. So we could infer a lot of causes for that, but all we're doing here is just looking at a picture. Now this information could have been given to you in a table. They could have given you the number of no alcohol related fatalities, moderate alcohol related fatalities, and high alcohol in a table. And you would have sat there, because I would have, and I would have stared at those numbers and said, okay, that's nice, but I don't see anything obvious that this is telling me. But when I make a picture of it, I can see a lot more. And what I actually have here is what's called a time series chart. The reason it's called a time series chart, even though it's also called a multiple line graph, is because this is how certain characteristics changed over time. Excuse me. Now, in these two graphs, I told you last time that I usually don't want a legend on my graphs, but in these two graphs, in order to understand the graph, you need the legend. The legend is what actually gives you the information that you're after. Now, this is called a stat plot. And on the left, we have the exact same information that we had on the last graph. What you see here is the yellow area represents the number of deaths in thousands where high alcohol was involved. And the ones where there was no alcohol involved, you'll notice that that covers up a significantly bigger area, which is, like we said on the last graph, the no alcohol related number of deaths were actually higher than the high alcohol for the most part. And notice that the moderate alcohol doesn't really make up a significant portion of the total number of automobile fatalities. Now this other graph that we have over here, and I think this one's on your handout, it's not as, if you're looking at the handout that you have in Shobi, I hope it looks a lot better than what it does on my handout, because when I printed mine out, this is what I got. So I hope that didn't happen to you. So this is what it should have looked like. And what we have on this side, excuse me, I would have thought the rain would have cleared this out. What we have here is we've got categories of public 2-year commuter schools, public 4-year in-state on-campus schools, public 4-year out-of-state on campus, and private 4-year on-campus schools. And we're comparing some budget items, but what we're comparing is a bunch of different budget items for the same different kinds of colleges. So you notice overall the budget for public 2-year community colleges or commuter colleges is about $14,000 compared to private, which is about $37,390. But notice that the biggest difference in all of these is the tuition and fees, the dark blue part of the bars. The primary difference is that tuition and fees. If you look at the room and board, well, room and board here and here, they are different, but the actual amount, that bar is only higher because it's stacked on top of the tuition and fees. So if you look at the area represented by the light blue, you see that tuition and fees in all of the schools is pretty close to the same, somewhere between $7,500 and $9,000. So it really doesn't change much.
On the automobile fatalities chart, if you have one of those lines or categories dips below and intersects with one of the lower categories,
Uh-huh.
how does it, will the program automatically restack or replot it where that doesn't happen?
It will, and if you look here at the beginning, notice there's 3 separate bands there, right? But if we go back to the graph, at the very beginning in 1982, your high alcohol was actually higher than no alcohol fatalities. And it stayed that way, looks like until 1983. So maybe for some reason that year, something happened that year and that changed. But notice when we go look at the bars, what they're totaling in every case is the total number of deaths. So the area of the graph is representing the total number of deaths, not the peaks and valleys. So the big thing here is what drives the difference in the cost of different colleges. It's not your room and board. It's not your books and supplies. They cost pretty much the same at any of the colleges. It's not your transportation, even though these people are driving a lot more. And notice that their cost is a little higher because it's $1,380 and here it's $1,010. And this is $1,010, but this last one's only $807, so maybe they don't have to go quite as far for entertainment, or more likely they're not going out to part-time jobs. And your other expenses, 1895, 1906, 1906, and 1397, those are really not appreciably different. So the big driving force in what causes private four-year campuses to be so much more expensive to attend is because their tuition and fees is so much higher. And there again, you could have gotten the same information in a table with a bunch of numbers, and it would have taken a lot more brain power to sort that out. Whereas with a picture really and truly does speak 1,000 words. And Excel makes all of these. All you have to do is have the table of data and know what to ask it for. What we have here are two different kinds of maps. The first one is a geographical data map. And basically what those different states are representing is the dark blue is 1,100 to 1,200 million BTUs per person that they're using in energy. And if you go to the purple, they're using from 200 to 299 million BTUs per person. So comparatively, they use a lot of energy in Florida. They use a lot of energy in Oregon, California, Arizona, Nevada, Utah, and Colorado. Now, they may or may not be using all the energy for the same reasons. The people in Florida, they're probably using that energy to cool off. And so, same thing for those here in Puerto Rico. So they're using that energy to cool off. California, if you get in Southern California, they're using it to cool off. Same thing in Arizona. Nevada, maybe not quite as much. Utah and Colorado, their energy costs are probably higher because they have, they just have high energy needs for the things that they do. That, and they have very few people, so that drives up the cost. When you have less demand, that's going to drive up your cost. But Oregon and Northern California's energy costs are probably high because of other things entirely, because if you don't know anything about the geography of the West Coast, really Northern California and Oregon, their temperatures are not really bad in the summertime at all. It's like mid-60s for the most part. But now in the wintertime in both of those, especially Oregon, because you're talking about getting into the mountains there, that it can get pretty brutally cold. So their energy is being taken up with needing to heat. And then notice here, Alaska. Contrary to what you might have thought, Alaska uses the least amount of energy. Why do you suppose that is?
Fewer people.
No, a lot of people are running generators. How heavily is Alaska populated compared to Florida and California and these other states? It's not. So if you have fewer people, you don't need as much energy, right? And notice here, where the area we are in the Southwest, we're the second highest. So we fall still in the upper 50%. Wyoming and North Dakota, same thing as Alaska. Their population density is much less than what they are, say, in the Northeast or the Southwest. And notice that it's actually relatively high up here in New England, but the reason it's so high in New England, I would suspect, is really bad weather and a lot of people. Really dense population. Now, your contour map is not, it's showing you still a map of the United States, but your contour map basically is showing you a map of temperatures. And it is a little interesting to compare the contour to the energy use map, because there's a lot of other factors going in there besides temperature. Contour map looks only at temperature. And notice here it says that the widely separated contours mean large regions that have nearly the same temperature. So it's kind of odd that all of these have almost the same temperature, but then again, not maybe as much as you would think, because that's the central part of the country. They don't have as much change in weather patterns as the coastal areas do. Their weather comes in from the West Coast. And notice here too, throughout the South, our temperature is pretty consistent from the Mason-Dixon line south to Florida. It only increases when we start getting into Florida. But pretty much all this area here has the same temperature. And notice here, it's closely packed contours mean a large temperature difference over a short distance. So if you live in Ohio, there's a 10-degree difference in this yellow part of the state. And notice here, this is where we are, in this little area down here. There's quite a bit of difference just in this area because we're in the mountainous area, and our temperatures actually are cooler then. Whereas the other side of Tennessee fits more closely with Alabama and Louisiana. We also have something called three-dimensional graphs, and I want to caution you about making comparisons with three-dimensional graphs because they can be very, very deceptive. Three-dimensional graphs, this one is talking about sonic mapping that traces bird migration. And it says sensors across New York State counted each occurrence of the nocturnal flight call of a bobolink to trace the fall migration on the night of August 28 and 29 in 1993. Wonder who funded that study. And the data showed the heaviest swath passing over the eastern part of the state. So the eastern part of the state is Oneonta, which would be this one. This figure shows an essay grade data, and this is the number of people that got A's, this is the number of people B's, this is the number of C's, D's, and F's. It actually has a three-dimensional appearance, but it only shows two-dimensional data. Now, the reason that's deceptive, if you compare only the face of these bars, you can see that a C is indeed the most frequent. There's not that much difference between the number of C's and the number of B's. But notice how it exaggerates the difference between the number of C's and the number of F's or the number of A's by looking at it in 3 dimensions, because that volume is deceptive. It makes those differences look a lot bigger than they really are. So we have to be careful with those.
So on that 3D, that sonic bird migration nonsense, there's like 4 axes of information. Wouldn't it be more efficient to do something else? You've got to spend
Yes.
20 minutes staring at this.
Yeah, that's one of those where if you give me the numbers, I would have been equally befuddled.
Right.
Yeah, I mean, I don't care for this graph, and the reason these graphs are in here is sometimes they'll use a graph to show you information, and it doesn't make the information clear because the people making the graph they understand the data, and they don't consider that other people that aren't as familiar with it don't.
Or they want their information, the information they want to stand up.
Yeah, they're trying to make their information show. And, you know, maybe that's not the best picture, and maybe it's not the most honest picture. So that's one of the things we're going to talk about in this too is, you know, just because you can make a graph doesn't make it a good graph. Okay, this is a combination graph. This talks about the ever-growing presence of women in the Summer Olympics. And notice that from 1900 to 1916, where there were no games, that it stayed pretty steady, and it really didn't change a whole lot up until right before 1940. In 1940 and 44, there were no games. Who knows why there were no games in 40 and 44? Right. Why were there no games in 1916? World War I. Somehow we managed with the other wars not to miss out on the Olympics. But notice after 1948, how fast the number of women in the Olympics climbed until you got to 2008. That's a commentary on the advancement of women in a lot of different areas, because this is the presence of women. The total number of women participating in 2008, they participated in over half. And there was close to, I would say probably around 4,800 of those. So there again, that's another one where you want to look at the key. You want to be sure and look at your axes. This is a time series of a sort because it shows how things changed over time. But it also gives you little pie charts that shows you the number of women participants in the Olympics that year. And the percentage of women participants is, I'm pretty sure, the purple. It's not the blue. Because in the early years, it would have been nearly all male. So you can see how the gender differences change over time, as well as the number of female participants. Now these are pictographs. Basically it's a graph, but it's made up of pictures. It's meant to catch your eye. The one on the cigarette smokers does a good job because it uses cigarettes and it shows the length of the cigarette as the percentage of people that smoke cigarettes. And notice that in 1975, more men than women smoked cigarettes. But as we come to 1995, that's almost equal. Even in 1985, it's almost equal. What was interesting to me looking at this graph is that from 75 to 85, the overall percentage of people smoking cigarettes dropped. But in 1995, it came up again. And I'd be curious as to know why that might have been. And I also like to know what it would look like for 2015. Would it continue to go up or down? I suspect down. The other one shows your three-dimensional bars for 1804, 1927, 1960, 1974, 1987, and so forth. And it talks about the world population in billions of people. And you can see that as the years passed, the number of billions of people did increase. There's something wrong with that graph on the left. Does anybody have any idea what might be deceptive about that graph?
The jumps in time.
Yeah, look in the time. 1804 to 1927. That first jump in time was over 100 years. The second jump in time was less than 40. The third jump in time was only 14. Then it was 13. Then it was 12. Then it was 13. So from 1974 on, it's pretty consistent. But what went on before 1970? We don't have a clear picture of that because we've only got 3 snapshots at a widely different time. When you think about graphs, you have to think about things like that. Because there's something vastly different going on here that we don't have a complete picture of from what we see from 1974 onward. So you shouldn't leave gaps in your data like that. Not without drawing someone's attention to it at least. That's an example of what we call a visual distortion. And pictographs can be very, very misleading because of that. If you're comparing the wealth with bags of money, what do you actually think the difference is between this guy's money and this guy's money? Looks huge, doesn't it? By the picture looks a lot bigger. Does that necessarily mean that this guy has, what, 4 times as much money? Probably not. Maybe twice as much, but probably not. You really can't tell because you don't have any numbers, you don't have any scales. It didn't give you an amount for the money that each one had. So there's no information. Both of these are terrible graphs. This is also visually distorted. What's wrong with that graph? If you looked at the graph and you didn't look carefully, and it says it's the salaries of men and women aged 16 to 24, and this is the men and this is the women, would you agree with me that men make twice as much as women do, just glancing at that graph? If you don't look carefully.
It's only 60 bucks in effect, 55 bucks more, it's not really.
Yeah, the whole difference here is, let's see, this is probably $375,
Yeah.
and this is $330. Yeah, not even $50 difference. Why does the graph make it seem like so much more?
Because their starting axis is 300 instead of 0.
That's right, they're starting their axis at 300. And the differences above 300 are incremented in tens. So really, if I go all the way down to 0, these 2 bars are not that much different in their heights. So if you just look at the graph and you don't pay attention to the scale, you get a very, very misleading picture. And it is entirely possible that the person that constructed that graph wanted to give you that impression. Okay, so always look carefully at the graphs. Here's a picture of the graph drawn properly. Look at the difference between the two. The one on the right shows you a real picture of the information in men's and women's salaries. You see that there's really not that much difference. Yes, women make less, but it's not a huge amount less. Certainly not. They don't make half as much as the men do, which is what this makes you believe. These are also visually distorted. What this first graph shows is the rate of increase with time in tuition and fees at 4-year public and private colleges. So here's your public colleges with the red line, and your private is the blue ones. Now the problem is it's not showing you the actual tuition and fees. It's showing you how much they increased. Okay? So basically what happened here is that the private colleges looks like they kept their costs down a whole lot better than the public colleges, but the truth is we don't know what they're increasing from. They have a common base point, But that base point's probably not the same for public colleges or private colleges. In fact, the common base point for both of them, for public colleges is probably down here, and for private colleges is up here. So if you're only looking at the rate of increase, it makes it look like public colleges cost a lot more than private for that one period of time, and they really don't. This one actually shows the change in time with the actual cost, not adjusted for inflation, of the tuition and fees at four-year public and private colleges. And here your same legend holds true. The purpley red color is the public and the blue one is private. That's a true picture. It shows that over the period of time from 1995 to about 2009, private colleges increased dramatically in their tuition and fees, whereas public colleges did increase, but not as much. This gives them a level playing field. It starts them both with their actual costs. So the moral of this particular story, Mark Twain said they're liars, damn liars, and statisticians. Okay? He was a bright man. That's the truth. I worked as a statistician, and a lot of times a statistician is pretty much obligated to present what who's paying their bills wants them to present. But if you have an ethical statistician, someone that's working, for example, for a charitable foundation that's doing research on whatever topic it is for that foundation, they're likely to be more honest in what they find. Medical research is likely to be more honest if it is conducted at universities. If they fund it privately, you know, we're talking about pharmaceutical companies here, you're going to get a biased picture. You get what you pay for. Okay? So read statistics and ask questions. I'm not telling you statistics are bad. I'm not telling you that they're wrong. I'm not telling you they're deliberate lies. I'm telling you to make sure that you read them with an open mind and ask questions like, where did you get the data? How did you get the data? Who performed the study? Who paid for the study? So ask all those questions. So at this point, we are ready to move on to section 4. I'm sorry, not section 4, that was where we were. Section 5. Question? Let me look and see what's there. That's what I was trying to get into my... Okay, yes, we're going to do correlation and causation. You're going to need both of these handouts. So I'll give you a couple of minutes to get those printed if you haven't already. Yeah, your actual handout, the one for correlation and causation is 3 pages. I'll find mine for the calculator. not print mine in the calculator.
That poor pages, I don't understand.
There are 4 for the calculator handout, the other one is 3. It alternates. It's